thank you for having me here. I'm Gang Liu. I'm currently a fourth-year PhD student at the University of Notre Dame. So I'm excited today to have this chance introducing our recent work, multimodal large language models for inverse molecular design with retrosynthetic planning. This work has already been accepted by the ICLR 2025. So we know that the large language model is very powerful at understanding and processing text instructions, and I use them almost every day to write code, rephrase sentence, and summarize paragraphs. So usually people say that it has internet level knowledge, so it can handle this common sense task very well. But in this work, we wonder, does the large language model already achieve the scientist level intelligence to design new molecules? Yeah, we studied this problem in this research. And just like what the question present, we want to ask language model, can you design a molecule? And we describe the property we want the molecule to have. And then we tell us what kind of structure the molecule may contain. Then we use this question to prompt the language model to tell us what the specific structure we can have for the molecule to satisfy these requirements. Typically, in previous studies, researchers already done some work like how to translate the chemical name to chemical structures. But in this inverse molecular design, small challenge is because, as we can see from the question, we don't know exactly what's the chemical name, what's the chemical structure. We only have a rough idea about what the molecule property is, what the molecule may look like. So typically, we can input this question into large language model and get some response. Then we can extract the molecular structure from this response. Typically, the large language model will output the molecular structure in the format of the smells string, like a sequence of atoms and bonds. Then with this structure, we can evaluate whether these molecules are useful and whether they are synthesizable or not. So slightly going into details, here we have two ways to ask the language model to give us answers. One is in-context learning, and the other is supervised fine-tuning. In the in-context learning method, usually we add some demonstrations of different pairs of question and answers similar to the new question, to the prompt. Then we ask the language model to give us answer. Language model will learn from the demonstrations to generate similar answers. And for the supervised fine-tunings, in this pipeline, we usually need to collect many more question and answer data pairs. Using this question and answer data pairs, we can fine-tune the large language model. Then we can ask the language model with new questions. Then with these two pipelines, we can evaluate the usefulness of the large language model in different inverse design tasks. Here are some results in our preliminary study. We first evaluate 10 large language models with in-context learning method and 4 different models with supervised fine-tuning methods. And we focus both on the drug design task and the material design task. In the drug task, we use 3 categorical properties from the molecule net, this benchmark, and we reported their balanced accuracy across 3 different properties in the left figure. And to compute this accuracy, we calculate the number between the input property and the oracle score of the generated molecules. And similarly, in the materials design task, we focus on 5 different polymer properties. They are continuous properties, so we reported the average mean absolute error. So here, from this figure, we can see a clear trend that even the best model from in-context learning method, supervised fine-tuning method, they may not be good as the very simple and classical molecular optimization method called the graph genetic algorithm, or graph GA. This graph GA will do multiple iterations of the mutation and crossover to design new molecules. So these results are very interesting. They like it tell us like if we want to use the large language model to do inverse molecule design, it probably may not be a good idea to use them directly. So, but this results also inspires us like the graph model is very powerful in processing the molecule data and to handle this inverse design tasks. So in this work, we want to study the synergy between the large language model and graph models. So recently, there have been many graph-based diffusion model developed for the molecules. In one of our earlier work, we introduced the graph diffusion transformer, a new kind of graph diffusion model that have been demonstrated very strong in the inverse molecular design task. So in this work, we want to study whether can we combine a graph neural network, large language model with different graph models. In this way, we can have a multimodal large language model. We call it Llamole. It will handle both the question answering and the inverse molecular design task. So how does this framework generally work? So typically, the large language model in the Llamole will first analyze the question. It tells us what kind of molecules we want to design. It describes specific, it adds details on the structures and tell us and to instruct the following graph model to design this molecule. Then the Llama will automatically activate the corresponding graph modules, such as the graph diffusion transformers I mentioned, to generate this new molecular structure. The model doesn't stop here. Like after generating the molecular structure, the large model will be continues to use to continue analyze the structure, tell us how to synthesize the designed molecules. It will output the reaction procedures, and then we use another graph module such as the graph neural network to tell us what kind of reaction template or formula we can use to synthesize this target molecule. But typically, we need many steps of the reaction because some of the intermediate reactants may not be available. They cannot be purchased from the market. So we need multiple steps to decompose the designed molecule into the reactant that are all available to us. Yeah, that's the general framework. Slightly going into details. First, when we have questions, we use the word tokenizer from the large language model to tokenize the text input into the text tokens, and then we use the pre-trained large language model decoder to do the autoregression in the text space, and it continues until we predict the next token as a special token. Here we call it a design special token. This special token tells the Llamole that we need to activate the graph diffusion transformer module to design new molecules. But before that, we add another special token called query. This special token will pass through the large language decoder to summarize the previous token into query vectors. Then, given the query vector and the property requirements, we can use the graph generation model to generate the molecules we want. And after it, we use a graph encoder to encode the molecule into the token, into a single token. This single token will be passed through the large language model decoder, and then we can continue the autoregression problem in the text space. And we continue the text autoregression and until the next special token is predicted. Similarly, we call it the retro token. It taught the large language model we need to activate the graph neural network module to predict the reaction templates. So before that, we similarly add some query tokens to summarize previous generated text data, and then this query vector plus the designed molecule structure will be used as the input of the graph neural network. The graph neural network will predict the probabilities of different reaction templates. The framework doesn't end up here. we see that different from the traditional classification problems in the reaction prediction problem, typically we can apply multiple different reactions to the same designed molecule. Yeah, here, for example, we have reaction 1 and reaction 2. And reaction 1 will decompose the designed molecule into reactant 2 and 3, reaction G2 and G3. And reaction 2 will decompose the G1 to the G4 and G5. But not all the reactions are immediately available or purchasable. So in this case, only G2 and G4, they can be purchased. They are available in our there are some predefined data set. But G3 and G4, they are not available. We still need to find a way to synthesize them. So which one we should choose to work first? It's not an easy task because we can see that we can organize this synthesize searching problem in a tree structure, and as the tree goes deeper and deeper, the branches will grow very fast in an exponential speed, actually. So we see that it's really, we should be very careful about choose the leaf node to expand the tree. So here we focus on the A-star algorithm. A-star is a very efficient searching algorithm. Like it will combine the estimation of the future cost to the existing cost to get this searching space. For example, so we can use the main difficulty in the A-star is about how can we design the heuristic scores. So here we can use the large language model in the Llamole to estimate how many remaining steps are there for the G3 and G4. Then we can convert the answers into some heuristic scores. Then we can add this score with the existing cost to get the total cost. And to choose the next leaf node to expand this tree, we want to minimize this cost. So suppose in this case, this G5, so we can select G5 as the next node to expand this tree. And then we can return back to the last slide to use the large language model, analyze how to synthesize the G5, and then we can use the graph neural network to predict a template again for the G5. We can repeat. You can see that we can repeat this expansion and selection, these two steps multiple times until finally we get a solution for the synthesized pathways for the designed molecules. Or we can also like set a time period so that the model can return us some failure status if we cannot find a solution in a fixed time. Yeah. So that's about the model design part in this work. Besides like model.
Sorry to interrupt. I don't know if you will explain it later, but going back to like the actual architecture, could you explain a bit more on on like how, say for example, the query vector goes as input to the graph DIT? Because if I understand correctly, the graph DIT should take as input like atoms, right? But here you're inputting some latent embedding.
Query vector is like the last layer of the graph large language model decoder, so it's a vector. Yeah. So graph DIT can take inputs of two parts. One is the property. Property is like a vector. Each element is the property value. For the categorical property, it could be 0 or 1. For the continuous property, it could be any number in the space, regression space. Yeah. And so basically, graph DIT take inputs of two vectors. Yeah.
Okay,
and then design the molecule. It didn't, yeah.
But the base model takes as inputs atoms, right? Like or like 2D coordinates, 2D graphs, sorry.
Graph DIT is kind of diffusion model. It will start from the random noise.
Okay, never mind.
Yeah.
Okay. And then for the graph encoder, could you explain that again, please?
Yeah, it's like a graph neural network. I will introduce later like how we construct a data set to pre-train this graph encoder. But generally, it's a graph isomorphism network. Yeah.
Got it. Okay, thank you.
Yeah. Thanks for the question. Okay, here is like here's like the data set. Here is the two data set we contribute in this work. Like we call it MoleQA and MolePair. The MoleQA is used to fine-tune large language model and evaluate the large language model in the inverse design task. And the MolePair as is used to like pre-train these graph models as we see in the Llamole. So basically for the these two data sets come from like different data sources, and we also use some quality control method to filter them. We can see that we collect data from the small molecule, from the polymeric materials. Also, we collect reaction data from the USPTO database. Yeah, for the MoleQA, like we have few steps to generate the question answer data sets, but generally we have around 139,000 question answers, and 126,000 are used to fine tune or are used as a training set in the supervised fine tuning or in content learning methods, and also 11,000 of the question answers are used to evaluate the large language model performance in inverse design. And another data set is MolePair. It consists of two parts: graph text pair to pre-train the graph generation models and the graph encoders. And there are also like 1.6 million reaction text pairs. They are used to pre-train the graph neural network to predict the reaction templates. Yeah, that's about the data set. Then we use this data set to pre-train we use the MolePair to pre-train the 3 graph model modules, and then we use the MoleQA to fine-tune the large language model. Yeah. And going into results here, we compare the Llamole performance with the best methods from in-content learning, from supervised fine-tuning, also from the graph generating algorithm. We can see that a clear trend that Llamole can improve the best performance. Yeah, on this graph design task, it can improve the best performance by about 15%. And in the material design task, the improvement is more significant, around 19%. So also in the retrosynthesis tasks, Llamole can also significantly improve the success rate. Usually we find that even the best large language model is struggle with the reasoning task in the retrosynthesis. They only have a success rate around the 5%, but Llamole can significantly improve this rate by to the 35% for the drug-related task and 17% for the materials task. So it has two indications. The first one is that Llamole are designing molecules that are easier to synthesize. The second one is that this algorithm in the Llamole can efficiently get the model to explore more options in the huge reaction space. Okay, in the application studies, like we study different inputs of the graph diffusion transformer, this module, to see how this graph generation model work with the large language model. Here we focus on 4 metrics. They are chemical validity, structural similarity, and drug-related balance accuracy, and the mean absolute error for the materials tasks. Here we have 3 variants. The cyan color denotes the full version, and the orange color represents the version we don't have the we don't use the large language model generated text condition as the input for the graph diffusion transformer, and for the blue color it represents we don't use both the text and property conditions. Yeah, from the first 2 figures, we can observe that the large language model can generate text instructions, and this text instruction then helps the graph diffusion transformer to better understand the chemical structures. And from the last 2 figures, we can see that the Llamole, this model will use the graph diffusion transformer's capacity to handle the property inputs so that it can generate molecules with desirable properties. Okay, we also analyze what's the reason or why the large language model fail in the retrosynthesis this task. Here we group different errors into 5 tags from instruction following to the generation correctness. And we can observe from this figure that for the in-context learning method, the typical question for them is that they cannot follow the instruction to generate reaction-related tags. But for the supervised fine-tuning method, they can follow instruction, but usually they don't generate templates. It means that we cannot verify whether the generated reaction formula is correct or not. Okay, that's all actually I want to share about the model design, data size, and the experiments result. Here, I want to use a case study to quickly summarize the Llamole methods. Given any of the question as the input, such as can you design or synthesize a molecule with some properties, with some structural requirements? Our model, the Llamole method, will first analyze the question. It will generate some answers like the molecule has a complex ring with two aromatic chains, blah, blah, blah. And then it will use the graph diffusion transform to generate the specific molecular structure, like in the figure. And it will continue to analyze how to synthesize these molecules. In this case, the procedure has 2 steps. And in each step, we use the large language model will tell us what's the reaction procedure, what's the pressure, temperature about the reaction, and then the graph neural network will tell us what kind of specific reaction template and reaction formula we should use. Yeah, that's about in this case study. But definitely there are some room to improve the models. If we look at the details, we see that for example, the large language model tells us the design molecule should have the aliphatic chains and a carboxyl group and amino groups. Well, we can, if we observe the generated structure, we can see that some of the requirements from the text, from generated text are already satisfied, like it contains aliphatic chains. Yeah, but some of them are not. For example, like the model tells us that there should be a carboxyl group, but actually in the figure in the generated molecule structure, we observe that there's no carboxyl group, there is a carbonyl group instead. So we see there is a small inconsistency, but usually it may have some, but a molecule structure, that small inconsistency may cause big issues. So in the future, probably we need to improve the graph diffusion model or any other generation model to make this generation strictly follow the text description. Okay, that's all I want to share. Thanks for listening, and we already released the paper code and the model ways, so welcome to Code to access them and test in your own case. And as a quick takeaway, we find that large language model can be augmented with domain model and tools. In this way, they can perform autoregression tasks in different space. And here we focus on the chemistry and the material tasks. But definitely we can use different domain model and tools to augment the ability of the large language model. Yeah, and specifically for this direction, for the chemistry dimension, it's we have a few observation from the existing results as a future direction. First, we can help large language model to better understand molecular structures. For example, we can use our data set or create more data set to align the graphing, to align the text representation from the large language model from any text encoder and with the graph encoder. Yeah, and also we can, another direction is that we can improve the graph diffusion transformers ability so that we can design molecules to more strictly and precisely follow the text instructions. Yes, that's all I want to say. I want to share. Thank you.
All right, thank you so much. Yeah, if anybody has questions, you can write in the chat. I can start. Actually, if you can go back to the case use case, the last slide, pretty much. Yeah.
Yes.
So this is a nice summary actually of the whole framework. So on the first paragraph, the molecule one, so you depend on what the LLM first tells you to make, right? Like you ask it some question and the LLM already knows, quote unquote, what to do. but it hasn't like it still needs to like process like do all the retrosynthesis and so on. So
Yeah.
you're like depending on that, right?
For the first part, for
Yeah.
the molecule paragraph, it generated use two models, like the text description, like the black
Mhm.
text, they are generated from LLM. But for the molecule one here, the red text, they are generated from the graph diffusion models. Yeah.
So
So
for
generally, we think that the idea is like large language model can like have some knowledge about the question. They may generally have the direction, the rough idea. They may add some details like what structure may look like, but they may not be able to like to design what is exactly the structure looks like.
yeah, so that means that the rest of the flow will depend highly on that text that was first generated, right? As
Yes,
if it was
yes, because
wrong, then you're
yes,
dead.
because the next paragraph is about the synthesis. It's about how to synthesize the design molecule. So if the design molecule is different, so the next paragraph will be different.
Okay, and by any chance, have you looked at like what the error propagation is? Because like again, like say for example, in that first paragraph, like let's say like only 30% yeah 30% of those paragraphs are wrong. So that means that later on everything will be wrong, right?
It's not about wrong or correct. It like uh it like in our like in this figure like we it's about wrong or correct. You mentioned about like more like the accuracy or the mean absolute error of the generated molecule and the
Yeah,
target you want to have. But
yeah, yeah, yeah.
for the retrosynthesis task, it's not about like it have no relation to the properties. Just like tell us how can we synthesize this molecule. So even if this molecule is wrong, we may still be able to synthesize them using some like reaction procedures. Yeah.
Okay, okay, yeah, that makes sense. So you start then, okay, you give it the LM, it gives you a text description. That text description gets embedded and then input to the diffusion model, which is like that molecule one in red, right?
Yes. Yes.
And so like you're conditioning the diffusion model on the latent of the LM plus the properties that you mentioned before.
Yes. Yes.
Okay. And okay, that's clear. And do you mentioned also like you stop the tree search when you find that all your reactants are available? Do you have like a database of available
Yes.
commercially? Yeah.
Yes. We use the enzyme database generally.
Okay.
You
Okay.
know, that's commonly you'll see many like searching, like reaction searching problem.
Right. Um. Yeah, it looks pretty clear to me. Pretty interesting work actually. Um.
Thank you.
Yeah. If anybody has any questions, okay. I guess not. Yeah, we can close it here then. Again, thank you so much.
Thank you.
Yeah, we will be uploading the YouTube recording, well, the recording to YouTube. And yeah, if you have any questions, I guess you can reach out to him, like on LinkedIn or in his email.
Yeah, no
Um,
problem.
and yeah, we'll come back next Thursday with more webinars. Thank you so much.
Thank you. Bye.
Bye,
Thank
everyone.
you.
Thank you.